today's goal is to get us back to this. Okay? To think about how to arrange the results of some operation that may be arithmetic, it may not be arithmetic. But having this at your disposal tells you a lot about how to multiply numbers. How does it work? So how do you use a multiplication table?
Go on the top to your first number.
Okay.
And then down to the second number.
And then down to the second number.
And then whatever is in that box is your answer.
Okay. Yeah. So yeah, we're getting there. So yeah, if we want to know where 12 times 12, if we want to know where 13 times 12 is located, you're all saying great things right now. Don't stop just because I'm talking, because yes, those are all things that we want to talk about. So 13 times 12, Cam says, well, find 13 up here at the top, and then go down to the row with 12 in it, and we get 156. But then, what was the other question that somebody just said?
What if it's a different operation that's not commutative?
If it's not there's two places we can find the answer to 13 times 12 in this table. One of them is right here. Where's the other one?
12 times 13.
Yeah, over here on the opposite side of this diagonal, right? And so what this times table is doing is it's showing us two potentially different multiplication problems, right? 13 here and 12 there versus 13 here and 12 there. And it just so happens that for multiplication of integers, those two answers are the same, because multiplication is what kind of operation? Commutative. Multiplication of integers is commutative. And so I think when we were first memorizing our times tables in elementary school, we probably didn't have to memorize this whole table. We only had to memorize maybe the top half of it, right? Because everything on the other side of the diagonal is the same as something on the other side, right? If we were still in linear algebra, and if this were a gigantic matrix, what kind of a matrix would it be? What do we call those matrices in linear algebra? Well, the diagonal is this yellow highlighted line right here. And the matrix that we would form, the 20 by 20 matrix, would be... It's a square matrix because it has the same number of rows as it has columns, but it also... Close. Try one more property we learned on Friday. Symmetric. We call it a symmetric matrix. Symmetric matrix is a matrix that is equal to its own transpose. The transpose being what we get if we exchange rows with columns, right? So this matrix would be a symmetric matrix because every element in the ijth position and the element in the jith position are equal to one another, right? The ith row, jth column, and the jth row, ith column have the same entry in them, equal to one another. So this is nice because if the numbers 1 through 20 are the only numbers that we care about in the whole universe, and if multiplication is the only operation we care about in the whole universe, then this is the beginning and the end of the story. This tells us everything about multiplying the numbers 1 through 20. Right? In fact, it tells us everything twice because of this symmetry property. So, as you might expect, we want to do this with groups. Right? We want to be able to take the elements of a group, array them down the first column and the first row of this table, and then inside the table, put all of the results of applying the group operation to the elements on that row and that column. But, as you've already noticed, we have to agree on something first. And we have to agree on where to find 13 times 12. Which one of these 156s do we find? Why does it matter, first of all? If we're talking about groups now, why does it matter? Not necessarily commutative. We can do groups, and we've already seen our first examples of groups this semester, the rational tangle group and the group of symmetries of a regular polygon. Neither of those had a commutative operation. And so for them, it matters what we decide on here. So what's the convention that the author of our book uses? Which one of these would be 13 times 12, the orange or the yellow highlight? Yeah, we're going to go with the yellow highlight. So the convention for our quote-unquote multiplication tables, which are now going to be called Cayley tables. Cayley gets a lot of stuff in abstract algebra named after him. But the convention is that we will find in a Cayley table the element g times h will be on the same row as G and on the same column as H. And that's the convention. Whoops, I got that. Put that in the wrong place. Same column as H. And so GH is going to be right here. Make sense? Okay, so that's the rules of the game. Okay, so that's how we are going to create a Cayley table for a group. And the groups that I'm going to have you working with today are, hopefully not coming as a surprise, given that I said that I want us to get more practice with modular arithmetic, they're going to be groups of modular arithmetic. So let's do a quick example of this together, and then I'll turn you loose in your groups today. So modular arithmetic. All right, so what I mean by modular arithmetic is that I want the operation in my group to be either addition or multiplication of integers, but not just integers ordinarily. I want let's take multiplication as our example. Multiplication mod 4. Just as an example, right? So in other words, this operation is going to take two numbers, G and H, and then it's going to form the product G times H mod 4. And to clear up a little bit of the confusion from the quiz that lingered a little bit over the weekend in our chats, when we use mod 4 in this context, what it means is there are really infinitely many different things that could be congruent to this mod 4. What we want to do is we want to pick the one which is the smallest representative of its equivalence class. So here's how I want to motivate that for a moment. If we take the integers, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, go the other way, 2, 3, negative 4, 2, 3, negative 8, and so on. So this is a picture of the integers, right? Is the black marked numbers on this number line. If I take the equivalence relation that says that two integers are equivalent exactly when their difference is a multiple of 4, and I'm going to write that in a different way here. I'm going to write that that difference belongs to the set of multiples of 4. 4, 8, 12, etc. Now, this is an equivalence relation of the type that we worked with on Friday, right? On Friday, we studied equivalence relations that were defined by the difference of two integers belonging to some set, right? And your job was to figure out what kinds of sets we could allow there to be in order to make that an equivalence relation. And you answered on Friday that whatever sets they were, they had to be closed under the operation of addition, they had to contain the identity element, 0, and they had to contain additive inverses for everything, right, inside of that set. And here is the set of all multiples of 4. Does that meet those three criteria? If I add two multiples of 4, do I get a multiple of 4?
Yes.
I do. Is 0 a multiple of 4? It's 4 times 0. And is the additive inverse of every multiple of 4 also a multiple of 4? Yeah. It's just the opposite multiple of the other one. So it satisfies all three of those properties. And therefore, this is an equivalence relation. So what do its equivalence classes look like? For example, what is the equivalence class of 0 in this? So if I want to know what the equivalence class of 0 is, I'm really asking which x are related to 0. That's how you define an equivalence class. It's a set of all x's such that x is related to 0. Or 0 is related to x, but since it's symmetric, those two are the same thing. Well, what does it mean for x to be related to 0 according to this? It means that x minus 0 has to belong to this set, right? So x minus 0 is a multiple of 4. I should call this set something. Let me call it A. It means that x belongs to A, the set of multiples of 4. Right? And so what does that look like? The set of all multiples of 4.
Yeah.
it's just A. So it turns out that that's always going to be the case, isn't it, for the equivalence class of 0, right? Because we know 0 always belongs to A. We insisted upon that to satisfy the reflexive property on Friday, right? And since 0 belongs to A, and everything belongs to one and only one equivalence class, that must mean that A must be the equivalence class of 0. So if I can use some colors to kind of color code stuff here, the equivalence class of 0 is where we're going to find all these red marked numbers, 4, 8, 12, -4, -8, and so on. Right? Okay, what about the equivalence class of 1? How would it be different? We know that it has to be disjoint from the equivalence classes of 0, right? Because equivalence classes can't overlap. So how does it change?
Change to like 1, 5,
Yeah.
9.
1, 5, 9, going the other way, -3, -7. Right, these are all the numbers which are one more than a multiple of 4, right? And so the equivalence class of 1, if I color code it some other color, let's say green, it includes 1 because of the reflexive property. Everything is in its own equivalence class, but it also includes 5, it includes 9, it includes -3, it includes -7. So all of the green marked points on the integers are part of the equivalence class of 1. All right, so we'll skip a few notational steps. What's the equivalence class of 2 going to look like? Shift everything one more to the right. These are going to be the numbers that are 2 more than a multiple of 4, which also happen to be 2 less than a multiple of 4, right? It happens to be right in the middle. And then finally, the equivalence class of 3.
So does that mean that the equivalence class of 2 is equal to the equivalence class of -2?
Yes, it absolutely does. Yep.
So in terms of 4, it's not that it's every even, it's that every half?
It's at every even that's not a multiple of 4 is part of the equivalence class of 2. Yep. Which is the same as the equivalence class of -2, which is the same as the equivalence class of 10, which is the same as the equivalence class of 402, which is the same as the equivalence class of -1,000,002. Yeah, that's got it right. So yeah, right. That's the great thing, is that how many equivalence classes are there? So I've got the equivalence classes of 0, 1, 2, and 3. What's the equivalence class of 4? So we don't need to list it. Right. The equivalence class of 4 is identical to the equivalence class of 0. The equivalence class of -1 is the same as
3, isn't it?
3. That's right. The equivalence class of -1 is the same as the equivalence class of 3. And so that's the thing about equivalence classes, is that any one of its members can stand in for all of its members. Right? And so when we ask for something mod 4, what we really are asking is, and it's the same as what you get when you compute the remainder when you divide by 4, which of these representatives, 0, 1, 2, or 3, is representing the equivalence class we're looking for? The set of all equivalence classes, which we'll write as this little, what's called a quotient. So we're quotienting this set using this equivalence relation. So if I list all the equivalence classes, we know we have to list the equivalence class of 0. We know we have to list the equivalence class of 1. We know we have to list the equivalence class of 2. We know we have to list the equivalence class of 3. But then Brian's question is, what happens if we also list the equivalence class of 4? Well, what happens when you're listing the elements of a set and you list an element twice? It's the same set, right? It's redundant with one another. So these two, the equivalence classes of 0 and 4, are the same, which means we can get away with only listing one of them, right? Same thing with any other equivalence class that I might write down here that's not being shown. The equivalence class of 68. Oh, great. Why did I choose 68? Would be the same as the equivalence class of 0, so I don't have to list it. The equivalence class of 71 would be the same as the equivalence class of 3, so I don't have to list it either. So one of the great things about an equivalence relation is that once we've passed to what we call this quotient, now we don't have infinitely many integers. We have only 4 elements in this new set. Right? And so now we can make a Cayley table, a multiplication table, in which we can see all possible results of multiplying and adding. Because it's just going to be a 4x4 grid, right? Where what I'm going to do in my Cayley table is I'm going to try to visualize what do I get when I multiply together, mod 4, elements from these equivalence classes. And so I wrote the operation first before I wrote the elements, because now these are what the elements are going to be. The elements are going to be these equivalence classes mod 4, 0, 1, 2, and 3. Okay. So that's going to be what I call my set G, and then my operation, G times H mod 4. And so we're just going to make a multiplication table with this information. Let me throw out one more metaphor for this before we get started. You'll notice that as you read this number line from left to right, we have this pattern that starts repeating itself, right? Red, green, orange, purple, red, green, orange, purple, red, green, orange, purple. So rather than thinking about these equivalence classes as being these infinite sets lying along a number line, what we can think of instead is that these equivalence classes of integers are just wrapping back around on top of themselves. So it's a bit like winding the number line around a circle, and then getting, in turn, the equivalence classes of 0, 1, 2, and 3. Just wrapping themselves around a circle. And this is the old clock metaphor, right? For, whoops, I used the wrong color for 2. This is the sense in which modular arithmetic is like arithmetic on a clock. Because as soon as we get to 4, it's the same as if we were still back at 0. 4 is the same as 0, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, and so forth. So what's the Cayley table going to look like? Usually in the corner, we'll put the operation. So I'm just going to put in here multiplication and then a little 4 in the subscript to denote that that's what we're doing. Say I wanted to find the entry for 3 operation 2. What am I really saying to do here? What arithmetic do I need to carry out? If I want to multiply 3 times 2 mod 4, well?
I don't know, then that has a remainder, or a mod of 3 and a mod of 2.
Okay. Well, so you're thinking ahead a little bit, Cam. Right, because so I could take any, I haven't proven this, but we could take any representative from those equivalence classes, and we should get the same answer when we do this problem. But let's be naive. Let's just take 3 and 2 as integers. Multiply them as integers, which we know how to do. And then ask the question, if the answer is 6, which of these equivalence classes does 6 belong to?
2.
Right. Right, because when I divide 6 divided by 4, I get 1 with a remainder of 2. And the remainder tells you which equivalence class you belong to. Right. So in my Cayley table, I'm going to put this 2 in here somewhere. Where?
The
Last row and in the 3rd column. Right, because again, keeping our order straight, G times H is going to go on G's row and in H's column. So down here in this entry, I'll put 2.